These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optics series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state or province, and country. Thanks, and enjoy the podcasts. This lecture deals with angular magnification. And I'm going to start out with a question for you. Let's say that I ask you how much magnification you were getting from a telescope. Let's say that you point the telescope at Saturn, and Saturn looks bigger, and I ask you, how much bigger does it look? Well, that's a difficult question. You can't really set it up as a transverse mag problem because you don't know what the distance is to Saturn. And let's say that you were able to set it up as a transverse mag problem, that you did know what the distance is to Saturn. What if I were to ask you how much larger a constellation is, where the stars in the constellation aren't even in the same plane? How are you going to describe what the magnification is that you're getting in that system? Well, one way you could do it is you could say, well, with the unaided eye, Saturn subtends X minutes of arc of my visual field, or X seconds of arc of my visual field. And with the telescope, it subtends more seconds of arc of my visual field. What you're describing is you're describing the angular magnification, how much of the visual field the object takes up. And it's angular mag that we use to describe the power of telescopes. So let's go ahead and do that now. This is an example of an astronomical telescope. And I want you to immediately recognize one thing. Let's do this as a vergence problem. With the rays of light coming in from Saturn, they're going to come in from essentially an infinite distance with a zero vergence. They encounter this +2 lens, and they exit the lens with a vergence of +2. +2, always and forever, means that the rays of light converge 1/2 meter, and plus means to the right. So the rays of light converge here. We're going to go an additional 1/10 of a meter from there, and we're going to say, what is the vergence of the rays of light here? Well, the rays of light converged 1/10 of a meter to the left. 1/10 of a meter means that the vergence is 10, to the left means minus. So the vergence of the rays of light striking this eyepiece, the vergence is going to be -10. The dioptric power of this eyepiece is +10, so the vergence coming out is 0. This is what I want you to recognize. Telescopes, 0 vergence in, 0 vergence out. So what is going on here in our terms? There's a real image of Saturn that is being formed here inside of the tube of the telescope. By the way, how long is this telescope tube? It's 0.6 meters long. When we look through the eyepiece of an astronomical telescope, the image relative to the object is upside down. I'm going to show you, using central ray tracing, why that's true. So we have Saturn here, and we have lens number 1, and we're going to do central ray tracing number 1. So we have the ray of light here, and another central ray coming from the top of Saturn, and the image is formed here. We know that from our previous vergence diagram. So we see Saturn here is upside down. The way that we describe the magnification in terms of the angle is we can say that the angle going in, sort of the visual angle, the unaided visual angle, or the visual angle going in, and this will be the visual angle coming out, the exit angle. So exit angle over entrance angle is equal to angular mag. Now, let's take another look at this telescope, and let's ignore the eyepiece. Let's ignore the plus 10 lens through which we would look, so that all that we have is a kind of a simple object lens image problem. We have the object here, we have an inverted image, and what I want to do is I want to get very close to this image in order to see it clearly. So let's say that I want to, let's say that I introduce a little screen here, and I'm going to project Saturn on that screen. And I want to get 1/10 of a meter from that screen. What add do I have to give myself so I don't need to accommodate and get 1/10 of a meter from the screen? Well, the answer is a plus 10 add. And you can view this eyepiece as if it were an add, allowing us to get close to this image. We can describe the magnification, the angular mag of an astronomical telescope as the dioptric power of the eyepiece, the plus 10, over the dioptric power of the objective, in this case plus 2. So 10 over 2 equals 5. This is a 5-power astronomical telescope. Now, what if I want to make it a 10-power astronomical telescope? I'm going to increase the power of the eyepiece from plus 10 to plus 20. And that means I'm also going to shorten the tube of the telescope because I need the vergence striking the plus 20 lens to be minus 20. The only way to do that is to decrease this portion of the telescope from 10 centimeters to 5 centimeters. So the entire length of the tube is going to go from 60 centimeters to 55 centimeters. But let's go back to the idea of using the eyepiece as if it were an add. I want to see the image twice as large in my visual field. Well, let's say that I have a 20/20 Snellen line up on a screen and I'm 20 feet from it. If I walk up to it so that I'm now 10 feet from it, for me it is no longer 20/20, it is a 20/40 line because it is subtending twice as much of my visual field because I'm only half the distance from it. Well, we're going to do the same thing with the eyepiece. If we go up on the eyepiece from plus 10 to plus 20, allowing us to get, rather than 10 centimeters from the image, we're going to be 5 centimeters from the image. Now that image is going to subtend twice as much of our visual field. But of course, in order to get twice as close to the image, I have to double the power of the eyepiece. So I want you to use that, to view the eyepiece as an add, as a way of visualizing why it is that doubling the power of the eyepiece is going to make the telescope twice as powerful. It's going to do that because it's going to let us get twice as close to this image that's inside of the telescope tube. And we're going to have to make the tube shorter to compensate for that. So astronomical telescopes, images upside down. We're going to contrast this with a Galilean telescope. Now this is what a Galilean telescope looks like. We have zero vergence in, and again we're going to have zero vergence coming out. But we have zero vergence coming in. It encounters the plus 2 objective. It exits the lens with a vergence of plus 2. Plus 2 means that the rays of light converge half a meter to the right. However, 10 centimeters before those rays of light converge, we're going to introduce a minus 10 lens, so that the rays of light striking this lens would have been converging 1/10 of a meter to the right, so they have a vergence of plus 10. They hit the minus 10 lens, the minus 10 eyepiece, and they emerge with a vergence of 0. Plus 10 minus 10 equals 0. Again, it's the dioptric power of the eyepiece over the dioptric power of the objective. In this case, it's the negative of the dioptric power of the eyepiece over the dioptric power of the objective. Don't sweat the signs because we don't really talk in terms of negative mag. So if you calculate it and it's a negative mag, you can just drop the negative sign and say, well, that's what the mag is. In this case, it's a 5-power telescope, just like the previous one. The length of the tube here is 40 centimeters. If we were to double the power of the eyepiece, the length of the telescope would go to 45 centimeters. and the power of the eyepiece would be minus 20, and it would be a 10 power Galilean telescope. Now, despite the fact that the telescopes that we use clinically, things like the slit lamp, do not invert the image, they are in fact astronomical telescopes and have a set of prisms in them to reinvert the image for us. They're not Galilean telescopes. We do run into Galilean telescopes clinically, and it can be in this case. Let's say that we have an aphakic patient. You remember way back when we talked about accommodation in ametropia, the case of the plus 10 hyperope. So let's say that this patient is, as a result of aphakia, is a plus 10 hyperope. And you'll remember that the refractive error at the corneal plane was minus 11.4, meaning that the patient would have to wear a plus 11.4 contact lens to achieve the same optical power that he's getting from his plus 10 spectacles. And that's because the spectacles at the spectacle plane. And if you are not following what I'm saying, then please go back and rewatch that lecture. But at any rate, the aphakic patient who requires a plus 10 spectacle or would require a plus 11.4 contact lens is equivalent to an emetropic patient who is wearing a minus 11.4 contact lens and a plus 10 spectacle over it. That patient is in essence wearing a Galilean telescope, where the power of the eyepiece is minus 11.4 and the power of the objective is plus 10. And so in this case that I'm giving you, this patient would have a telescope that is 1.14 power, or would be seeing things 114% the size that they really are, 14% larger. So we don't use Galilean telescopes intentionally, but we do sometimes run into them in our practices. Yes, and that's a picture of Saturn there. And as I said, the image is upright in a Galilean telescope. Once more, we have the entry angle and exit angle. And again, the formula is just about the same thing. It's the negative of the dioptric power of the eyepiece over the dioptric power of the objective.